Hello, AP Chemers. Hope you're having an amazing day. We're going to continue our notes with calculations with the equilibrium constant. Some of you, we've already done this one with the NOCl. Some of you are about to start this one. So I'll go over this one again just in case, but if we already covered this one in your class, you can go ahead and move forward to the next one. So we want to calculate K at 25 Celsius for the decomposition of NOCl. We're given that we have 2 moles of the NOCl in a 1 liter flask, so it's 2 molar. And then it's allowed to sit there and reach equilibrium. And in the equilibrium system, the concentration of the NO is given to us as 0.66 molar. So first thing you want to do as soon as you see equilibrium is write the KEQ expression. So KEQ is equal to the concentration of NO squared times the concentration of Cl2 over the concentration of NOCl squared. Next, we're going to plug in our values. So we're given 2 moles of NOCl and it's 1 liter. Problem is, we can't plug that in here because these have to be the concentrations at equilibrium. In the question, it tells us that 2 moles of the NOCl are placed in the 1 liter flask, and then it's allowed to reach equilibrium, which means that the 2 molar, that's your initial concentration, not the equilibrium concentration. So, excuse me, if you don't have the equilibrium concentrations, that means you have to find them out some other way, and that way is usually an ice chart. So to do an ice chart, you write out your equation, so 2 NOCl yields 2 NO plus Cl2, and you write ice next to it. Ice stands for, the I stands for initial, C stands for change, and E stands for equilibrium. So basically, an ice chart takes you through the reaction. Initially, you can do this in concentrations like molar or in moles, but you put your initial concentration, so at the very beginning of the reaction, then what changes happened, did your concentration increase or decrease over time, and by how much, and then the equilibrium would be at the very end, is basically the net of the initial and the change. So let's start with the initial. So initially, it tells us that we have 2 moles of NOCl in 1 liter, so that's 2.00 molar. Your products at the beginning of the reaction are not there. You have 0 products. You haven't started your reaction yet, so this is 0, and this is also 0. The only other number we're given is that 0.66 molar, and that tells us that's the NO concentration, so it goes here, and it tells us that that's the systematic equilibrium. So it would go under equilibrium with the NO. So right here, you would put 0.66 molar. Now, if you started initially for NO with 0 and you ended with 0.66 molar, that means that the change was that you increased by 0.66 molar. If we know the change for the NO, we can figure out the change for the Cl2 from the stoichiometric ratio. It's a 2 to 1. So if I increased by 0.66 molar for the NO, then I would increase by 0.33 molar for the Cl2, because that's a positive sign there, because it's a 2 to 1 ratio. And if you look at the NOCl, because it's a 2 to 2 ratio, which is a 1 to 1 ratio, then this would decrease since it's a reactant. It gets used up by 0.66 molar. Then the equilibrium concentrations would be the net of the initial and the change. So you add these two together, you add these two together, and you add these two together. So at equilibrium, this would be 1.34 molar. This we already figured out is 0.66 molar, and then this one is 0.33 molar. Now that you have the equilibrium concentrations, these are the concentrations that you plug into your KQ expression. So let's do that. So KQ then is equal to concentration of NO is 0.66 molar, that's squared, times the Cl2 is 0.33 molar, divided by the NaCl is 1.34 molar, and that's squared. That ends up being 0.080 is our answer. And again, we don't care about the units for KQ. This number is less than 1, so that tells us that this reaction is reactant favored. That means there are more reactants at equilibrium than there are products. Okay, let's move on to the next one. It says we have 2 moles of H2 and Cl2. They're placed in a 4-liter container. So 2 divided by 4, so half molar for each the H2 and the Cl2. They give us K, it's 1.52. We want to determine the equilibrium concentrations of all substances for the reaction. First thing you want to do, write your KEQ expression. So let's do that. So KEQ is equal to the concentration of HCl squared divided by concentration of H2 times the concentration of Cl2. Okay, well, they give us the KEQ. They tell us 1.52. They want the concentrations at equilibrium, so the equilibrium concentrations of all the substances in the reaction. And they don't give us any of them. They do tell us that we have 2 moles in 4 liters, which is half molar of the H2 and Cl2, but that's at the beginning of the reaction, so that's initial. So in that case, you do an ice chart. So let's do an ice chart. So since my reaction is written right here, I'm just going to do the ice chart under it here. So ICE. So initially, I know that this is 0.50 molar, and this is also 0.50 molar, and that I don't have any products at the very beginning, so that should be 0. I'm not given any other information, so I need to try to figure this out. So I don't have any of the changes, but let's say that H2 decreases by X, since I don't know what amount it decreases by. I don't know what the change is. So I'm going to say this decreases by X, so minus X is my change. Excuse me, if the H2 decreased by X, then the Cl2 would also increase by X, and the HCl would increase, but it would increase by 2X because it's a 2-to-1 ratio from the stoichiometry in the reaction. So then the net, which is my equilibrium, this is 0.5 minus X, 0.5 minus X, and this is, it's a minus there, and that's 2X. So I'm going to go ahead and plug this back in here. So the HCl concentration, that is 2X, but then that's squared. Be careful that the quantity is all squared, so it ends up being 4X squared, not 2X squared. And then divided by my H2 is 0.5 minus X. That's 0.5 there, sorry. And then this one's also 0.5 minus X. And then you solve for X. Now that's pretty hard to solve for. The math is quite difficult there. So what I'd like you to do is, there's different ways to solve it. If you already know how to solve it, that's great. Go for it. If you don't know how to solve it, then go ahead and look at the very back of your packet, the very last page. It gives you 2 different ways for doing it. If you look at the back there, it says how to solve quadratics using graphing calculators. And then it gives you 1, 2, 3, 4 steps, and then it says, or using equation solver. Some of my students told me about the equation solver. I was never able to work it out on my calculator, but it's a much simpler way to do it. So if If you can figure it out on your calculator, great, use that. If not, then use the steps 1, 2, 3, 4. That's what I usually use. Or if you know a better way, by all means, please let us know and help us out. Or you can ask your math teacher for help with that. So the way that I do it is I take out my graphing calculator and I plug in, if you look at step 1, it says put for y1. So, when you graph a function, your first function is going to be the quadratic part, and you want to use parentheses for it. So quadratic part means this part, this whole thing. So enter that whole thing into y1. Okay? Then for y2, you enter the number, the KQ value. You enter 1.52. So I'm going to give you a minute to go ahead and enter that into your calculator. So this whole thing goes into y1. Again, make sure you use parentheses there. And then 1.52 goes into the decimal part. Okay? For your window, sometimes you don't really have to change your window. Other times you do. Depends on what your window is already set to. So if you look at step 2, it says set your window for x minimum is 0. X max should be a value that won't give you a negative number for molarity. So, maybe 0.5, because you can't have x to be higher than 0.5, in this case, for example. Then you want to set your y minimum and maximum so they encase the y2 value from step 1, which is this number right here. Then hit second calc and then number 5, which is your intersection, to find the intersection. So it's going to ask you, is this the first curve? You hit enter, if it's the correct curve. Then it'll ask you, is this the second curve? You hit enter. Then it will say guess, hit enter again, and then it will give you the answer. And the answer is obviously the x value is what you're looking for, because we're solving for x. So I'll give you a minute to do that, if you have a graphing calculator handy. Okay, so I got x to be 0.19 molar. Hopefully you got the same answer there. So then, if you wanted to solve for the concentrations, so you want the H2 concentration, which is equal to the Cl2 concentration. Both of them are 0.5 minus x, which is 0.5 minus 0.19, so that's 0.31 molar. And then you also want the concentration of the HCl, which is 2x, so that's 2 times, 0.19 molar. So that's equal to 0.38 molar. And so we got all of the concentrations. Okay, on to the next page. That should say for special, right here. That's a typo, sorry. For special reactions, we saw that KQ could be called K or KC. KC stands for concentration, KQ stands for equilibrium constant, or just K as the constant. Sometimes, instead of calling it KQ or KC or K, we give it a special name if it's a special type of reaction. For example, let's look at this first one here. We have ammonia in water. Ammonia is a special type of substance. It's a base. So when it's in water, it dissociates, you get NH4 plus and OH minus. And so this is a base dissociating in water. So this is base dissociation. And so instead of just calling it KQ, we give it a special name, we call it KB. But it's the same thing as KQ. It's the products over the reactants raised to their power. So it'd be the concentration of NH4 plus times the concentration of OH minus over the concentration of NH3. Remember, we don't put water in because it's a liquid. So this is the KQ expression, just we give it a special name. It's KB, that stands for the base dissociation constant. What if you have an acid? So let's look at the next one. This is an acid in water. This is acetic acid in water. So you get the acetate ion and the hydronium ion. So this is an acid dissociation reaction. So it's a special type of reaction. And so instead of just calling it KQ, which you can, a lot of times it gets the symbol or the abbreviation Ka for acid dissociation constant. But again, it's the same idea. You take concentration of the products over concentration of the reactants raised to the power of their coefficients. So concentration of the acetate ion times concentration of the hydronium ion, the H3O plus, divided by the concentration of your acid, the HCOOH. And again, we don't include the water because it's a liquid. The next one is really special. This is water. Water is covalent, so it doesn't really have ions that it dissociates into, but because of the extreme polarity of water, a very, a very, 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 very minimal amount of water does dissociate into H plus and OH minus, or H3O plus and OH minus, same thing. And so this is special again, and this is called the water dissociation reaction. Water dissociation. And so again, instead of just giving it any name as KQ, we give it a special name. So instead we call it KW for water. It's the water dissociation constant. But like always, products over reactants raised to the power of their coefficients. So concentration of the hydronium ion, the H3O plus, times the concentration of the OH minus over the concentration, not over anything, just the hydronium and the hydroxide, because water is a liquid, so we don't put in the expression. So it's just H plus times OH minus concentrations. Next, another special type is when you have an ionic substance, which we call salt. So this Na2SO4 is ionic, so we call that a salt. This is a salt dissociating in water or dissolving in water. You can call it dissociation or dissolving. So whenever you have an ionic substance dissolving, that gets a special name. We call that KSP. You'll see why in a second. As always, it's the concentration of the products over reactants raised to the power of their coefficients. So concentration of Na plus squared times the concentration of the SO4 2 minus. And then we don't include the Na2SO4 because it's a solid. We don't include the water because it's a liquid. This is called, excuse me, this is called KSP. Stands for solubility product constant. So solubility, the S is for solubility because you have something dissolving, so solubility. Product, because it ends up being a product, it's always multiplied, never divided by anything. There's never a denominator because these are always water, which is a liquid, and then a solid. So we never include a denominator in this, so that's why it's called product. So solubility, product, and then K for constant, so KSP, K with sub SP. So these are all basically KQs. They just get special names because they are special circumstances. So all these Ks are constants. They tell us what the concentrations are, the ratio of concentrations of products to reactants at equilibrium. K is always going to be a constant as long as your temperature is the same. I know here it says pressure and volume remain constant. Actually, don't worry about that. I would cross that out right here. K remains constant at the same temperature. If you change the temperature, K changes. If you change the pressure or the volume, K does not change accordingly. So if you have additional reactants or products, if you change the concentration, K will remain the same. So K remains the same always unless you change the temperature. Temperature is the only thing that will change it. If you have K for a reaction, and you know its value, you can figure out what K is for the reverse reaction because it's going to be the inverse or the reciprocal of the forward. So K reverse, K for the reverse reaction, is 1 over K for the forward reaction. So if we wanted to look at this equation, again, you know, all equilibrium constants are for reversible reactions. So this is water decomposing into hydrogen and oxygen. If I wanted to write the equilibrium expression for the forward, which is the one that goes to the right, so K, I'm going to write F for forward, is equal to the concentration of the H2 times the concentration of O2 over the concentration of H2O. And then don't forget to square your H2 concentration and your H2O concentration. If I wanted K reverse for the reverse reaction, so combining H2 and O2 to form H2O, it would be 1 over that. So you basically flip it. Now this is your product and these are your reactants. So it'd be the reverse of what we have written here, or the reciprocal of it. So that would be concentration of H2O squared over the concentration of H2 squared times the concentration of O2. What if you're changing the coefficients? So let's say that you have this reaction right here. Sulfur plus 3/2 O2 yields SO3. So let's try to write K for this one. So K would be equal to the concentration of SO3. It's a 3 there. Divided by concentration of O2 to the 3/2 power. We don't include the S for solid. If I wanted to write K for this reaction, it's exactly the same reaction except it's multiplied by 2, right? So let's do that. So that is equal to the concentration of the SO3 squared over the concentration of O2 cubed. Look at the two K's. Doubling your reaction, multiplying it by 2, will make the equilibrium expression squared. If you triple it, then the equilibrium expression would be cubed. If you quadruple it, then the equilibrium expression would be to the power of 4. So doubling the coefficients, you square K. So whatever you do to your reaction, your coefficients, you do that to the power of K. All right, what if you add two reactions together? So let's look at these two reactions right here added together. We have S plus O2 yields SO2. We're given K for that one. We're also given SO2 plus half O2 yields SO3. We're given K for that one as well. So let's add the two reactions together. If you add those two reactions together, you can cross out the SO2s since they're in both sides of the equation. So you'd end up with S solid plus an O2 and a half O2, that's 1 1/2, which is 3/2 O2 yields SO3. If I wanted to write K for that one, let's call that K3. That would be the concentration of SO3 divided by the concentration of O2 to the 3 halves. Again, we don't include S for solid there, but the O2 and the SO3s are gases, so we include them. Now, if you look at that, what we basically did was we took K1 times K2. So let's look at K1 here. K1, if you write your expression, would be SO2 concentration over O2 concentration. K2 is the concentration of SO3 divided by the O2 concentration to the 1/2. So if you took K1 times K2, that's going to give you K3. If you took this expression times this expression, you would get this expression. So whenever you add equations, you multiply their case. Let's write that down. When reactions are added, K's are multiplied. So if you wanted the actual value for K3, you would say K3 is equal to, like we said, K1 times K2. So then K3 would be equal to those two numbers multiplied by each other. So 4.2 times 10 to the 52. Wow, that's a very product-favored reaction. Times K2, which is 2.6. That's a 2.6 there. Times 10 to the 12th. That ends up being 1.09 or 1.1 with sig figs times 10 to the 65th. So that's an even more product-favored reaction. So when you add your reactions together, you multiply your case. All right, next topic we're going to talk about is Q, capital Q. Remember, we had lowercase q, which is heat. Capital Q is called reaction quotient. Quotient is means like when you divide things, so product when you multiply, quotient when you divide. The reaction quotient is just like KQ, it's just like K, the equilibrium constant, except we don't know if we are at equilibrium or not. K is only used for equilibrium, Q is used for anywhere in your reaction. And the reason why we have Q is so that we know whether the system is at equilibrium or not. So if you want to know if your reaction is at equilibrium or not, or if it's not at equilibrium, which direction would it proceed? Is the forward reaction going to be faster, or is the reverse reaction is going to be faster until it reaches equilibrium? Then you would use Q. So if you had a reaction where A plus B yields C plus D, Q would be just like KQ. It would be the concentration of the products raised to the power of the coefficients divided by the concentration of the reactants raised to the power of their coefficients. It's exactly like K, except you can stop the reaction at any point and plug in your concentrations. So these concentrations could be the initial concentrations, they could be halfway through the reaction, they could be at the end of the reaction. It doesn't matter. So you can stop the reaction at any time. Stop reaction at some point and measure the concentrations of your products and your reactants, and you plug them in. You calculate it just like K, just like your equilibrium constant, but you don't know if you are at equilibrium or not. You might be, but we don't know. And so that's why we use Q. Q will tell us whether we're at equilibrium or not. How can it tell us? Well, if Q, when you calculate it, so at any given point you stop your reaction, measure your concentrations, plug them in here. If when you calculate Q it turns out to be equal to K, then that means you are at equilibrium. If Q is greater than K, remember Q or K are products over reactants. They are concentration of products over the concentration of the reactants. Raised to the power of their coefficients, of course. So K is at equilibrium. So if your value for this is greater than what it should be at equilibrium, that means this value is too high. It's greater than what it should be at equilibrium. And so that means there's too many products. Your numerator is too high. So that means your system is not equilibrium. The ratio of products to reactants is too large. You have too many products. And so your reaction or your system will shift to the left to make more reactants. So that means that the reaction, the reverse reaction, going to the left, will be faster until you reach equilibrium. Okay? You're going to produce more of the reactants in order to reach equilibrium. If your Q value is less than K, that means this ratio is smaller than what it should be at equilibrium. Your system is not at equilibrium, then the ratio of products to reactants is too small. This value is too small, which means that you have too many reactants. And so to get rid of those reactants, you got to shift to the right to make more products so that your ratio of products to reactants goes back to what it should be at equilibrium. Okay, so if Q is equal to K, system is at equilibrium. If Q is greater than K, then you have too many products, so it's going to shift to the left to make more reactants to make up for that. If your Q is less than K, that means that you have too many reactants, so it's going to shift to the right to make more products to balance that out. So let's try a problem here. It says we want to consider the reaction for the decomposition of PCl5 into PCl3 and Cl2. They give us the value for K at 250 Celsius. They give us the concentrations of Cl2 and PCl3 and PCl5. So they give us all the concentrations. They don't say these are the equilibrium concentrations. They just say these are the concentrations right now. We want to know, based on that, is the reaction at equilibrium? And if it's not, which way will it proceed until it reaches equilibrium? So first thing you do is always write your Q or K expression. In this case, because we don't know we're at equilibrium, we're going to call it Q instead of K. So you call it KQ if you're at equilibrium. You call it Q if you're not sure. So your Q expression is going to be products over reactants raised to the power of their coefficients. So concentration of PCl3 times concentration of Cl2 divided by concentration of PCl5. We're given the values, so we're going to plug them in. PCl3 is 0.30 molar. Cl2 is also 0.30 molar. And PCl5 is 3.0 molar. When you plug this into your calculator, you get 0.03. So this is your value for Q. So then you compare it to the value for K. Our K value is 4.0 times 10 to the negative 2, which is 0.04, right? So 0.03 is smaller than our K, which is 0.04. So that means ratio of products to reactants is too low. It's smaller than it should be. At equilibrium it should be 0.04, but right now it's 0.03. So that means this number is too small, which means you have too much PCl5, so it's going to shift or proceed to the left. So this means you have too many reactants. You have too much BCl5 basically. So reaction proceeds to the right in order to reach equilibrium. All right, let's try another one. So the next one says 2 moles of bromine gas are placed in a 2-liter container at 1750 Celsius. The bromine gas dissociates 1% into bromide ions at equilibrium. We want to calculate K. Kc basically is K. All right, so first thing you want to do is write your KQ expression or your Q expression, whichever you want. So in this case, we're trying to find Kc, so we want to write the expression for Kc. So let's do that. So Kc or K, whichever you want to call it, is products over reactants concentration raised to the power of their coefficients. So Br minus concentration squared divided by the concentration of Br2. Okay, well, it doesn't tell us what the concentrations are at equilibrium. So what do? We do an ice chart. So my reaction is written right here, so I'm going to just do the ice chart right underneath it here. So ice. All right, let's figure this out. So initially, it says I have 2 moles of bromine in a 2-liter flask. So 2 moles divided by 2 liters, that's 1 molar basically. So my initial for bromine is 1 molar. Initially, I have no products, so that should be 0. Now, it doesn't tell us anything else except that the bromine dissociates 1%. So that means that this loses 1%. 1% of it dissociates. 1% of it is gone, turns into Br minus. So that means that this changes minus 1%. So 1% is basically 0.01 molar. 1% of 1 is 0.01. So that means the change for this one is going to be positive. And because it's a 2-to-1 ratio, the change would be double this one. So if the change for here is negative 0.01, it's going to be positive 0.02. So then this is 0.99 molar. You add them together. This is 0.02 molar. So then back to my K expression. So Br minus is 0.02 molar squared. By the way, I don't have to put the molar in there since we don't care about the units for K. Br2 is 0.99 molar. Plug that into your calculator. You get 4.0 times 10 to the negative 4th, and that's our answer. Okay, so in this case, this was K. So at equilibrium, the product to reaction ratio is 4.0 times 10 to the negative 4th. That's a small number. It's less than 1, so that means it's reactant favored. That means there's more reactants at equilibrium than there are products. All right, let's try one more. It says the equilibrium constant for AgCl, solid, dissociated into Ag plus and Cl minus, is 1.8 times 10 to the negative 10th. Remember, that's the one that's called KSP. You're dissolving a solid there. But again, you can call it KQ, you can call it KSP. It's the same thing. It's fine. So it says if the Ag plus concentration is 1.0 times 10 to the negative 5th, what is the Cl minus concentration at equilibrium? First thing you do, write your K expression. So, you choose either K or Q. In this case, we're talking about equilibrium, so you can use K. So we'll write K here. And just for fun, I'm going to call it KSP so that we're more proper. So the expression is concentration of Ag plus times concentration of Cl minus. And that's it. We don't put the solid in. Okay? Well, we are given K, or KSP. It's 1.8 times 10 to the negative 10th. That's pretty low. That means that this is not very soluble, because that means that this is, reactant favored because it's so small. That means there's not very much products there. Anyway, so 1.8 times 10 to the negative 10th, that is equal to, they tell us the Ag plus at equilibrium is 1.0 times 10 to the negative 5th. And they want the Cl minus concentration. So we just divide the KSP by 1.0 times 10 to the negative 5th. So the Cl minus concentration then is equal to 1.8 times 10 to the negative 5th. Don't forget to put units, that's molar. All right, that's it for today. Hope you have a wonderful rest of your day. See you tomorrow.